All right, hello and welcome everyone to Express Insight. The ultra-high-speed Phantom TMX is here. My name is Ethan Stokes and I'm a technical account manager with Trilion Quality Systems, and I'll be the moderator for today. If you have any questions during the event, please send them in the chat and we will address them during the Q&A session at the end. Now it's my pleasure to introduce the speakers for the day, Dr. Kyle D. Gilroy and Charles-Olivier Amyot. Dr. Kyle D. Gilroy attended the College of New Jersey to obtain his undergraduate degree in physics. After earning his PhD in engineering, he worked as a postdoctoral appointment at the Georgia Institute of Technology, where he researched in the area of nanomaterial science. In early 2018, he joined Vision Research AMETEK as an applications engineer, where he works on application development, and he travels internationally to consult on high-speed imaging applications spanning biomedicine, aerospace, ballistics, material science, and fluidic dynamics. He also manages the Phantom Academy of High-Speed Imaging, where he holds advanced application-specific short courses. Charles is the West Coast Regional Sales and Engineering Manager at Trilion Quality Systems, the North American distributor of GOM, world leader in optical metrology and digital image correlation. He started working in the field of material engineering at Laval University for the Metallic and Composite Materials Laboratory. After focusing on CFRP characterization in the aerospace industry for a few years, Charles then moved on to work primarily with North American companies and universities in aerospace, automotive, biomedical, and consumer electronics industries. He is continuously on the lookout for new developments from Trilion's partners to integrate and implement state-of-the-art optical measuring solutions in the pursuit of material engineering innovations and product development revolutions. At this point, I'd like to hand it off to Charles to get started.
All right, thank you very much. I'm really happy to have Kyle with me today. This is going to be a really interesting webinar. We're kind of short on time. We ended up having a little bit too much content for today's presentation. But hey, we're here to talk about the brand new Phantom TMX camera with very high throughput. I'm going to dive right in and explain to you why we think these cameras are interesting and are opening up a new market, but also what exactly did we do with them. So we use them to do digital image correlation. So in other words, do 3D optical strain measurements using only 3D cameras, so a pair of cameras to reproduce the images in 3D space. In short, what digital image correlation is and what's the algorithm that we use to process the images is simply based off, like I said, the pair of cameras in 3D space that we can calibrate and mount together. And we can project, just like a GPS, locate or triangulate any points of contrast in an image into the second picture to find exactly where the point is in 3D space. There's a couple of ways that we can do this. The first one is using point tracking with these black and white stickers. And you can see here on the prosthesis, we're tracking the XYZ motion of every single point where we have a sticker. So we're getting coordinates as the part is moving. Okay. We're also, because this is all optical and non-contact, we can get the displacements relative to one another from different things that are in the field of view. In this case here, you can see we have points also on the tip of the knee, and we're actually looking at the motion of the blade of the prosthesis relative to that knee dynamically. So this is differential motion. So how is the blade moving relative to the knee as the whole assembly is moving together in 3D space? Now we can also do a more classic digital image correlation processing, which use speckle patterns, so black and white spray paint. And I'll show you what we did here on a couple of parts and how we use that patterning to process the high-speed data. But essentially, this gives us a really strong and tight mesh of points where we can track thousands of data points across the field of view and see how each of them is moving relative to one another. Okay? The most frequent benefits of why we use this technology and why it was relevant here to try to deploy this on these brand new cameras is because we typically get non-contact, which helps us accelerate the testing, but also it's sometimes difficult to have contact sensors that will go at these speeds too. It gives us full field information, so instead of having a couple of accelerometers on the parts, we can have thousands of accelerometers here. Every location that we have XYZ coordinates can be translated into velocities or accelerations. It's an all-in-one box, so as we're getting strains, we can also get accelerations, and we can also get vibrational data by transferring all of this into the frequency domain. It's pretty flexible, so you'll see actually in today's examples, we did a couple of shots, and we did some shots in smaller and bigger volumes, but also at different resolution using different architectures of the sensor, allowing us to really have, with a single pair of cameras, a really wide range of application possible. It's also material independent, so we did some stuff on glass here, mainly today, but you can use this on any other materials. As long as you have contrast, then you can measure. Finally, static and dynamic, you're going to see here really dynamic tests, but the scale of speed is really dependent on the cameras that you can use. And this is kind of key here because actually the cameras that we use, Kyle's going to talk about them in just a minute, really are changing the maximum speed that we can reach with the throughput that they can achieve. Motion compensation, allowing us to eliminate motions of the cameras or vibration of the cameras. And really the fact that this is designed to adapt to whatever experiment that we have. We could add more or less cameras or switch the camera model based on the experiment that we have at hand. Okay? All right. There's no one single applications to talk about here. We can use digital image correlation for pretty much anything that you can think of. If you can see the part and you can film it fast enough, then you can quantify its displacements and strains as the test is going on. I want to go straight into the applications because, like I said, we're kind of short on time, and talk about what did we do with these cameras this week. So we started by doing some glass impact at 75,000 frames per second. Then we did a ballistic test where we fired a bullet and looked at it at 300,000 frames per second. And then we did also a shear of mirror, an impact from the side, and an impact of a smartphone. Now, I'm going to start by just showing you here the patterning method. So how did we pattern these different components? So you can see here we have light bulbs that we use for the ballistic test. We also have panels of glass that we use for the impact and for the shear. And the smartphone's not in this field of view, but you're going to see here just how we did the patterning.
All right, so now that we're in here, we're simply going to apply some spray paint, some flat white and flat black. First off is just some flat whites to make sure that we don't have any glare anymore on the surfacing, especially since we're doing glass. That's it, the white's done. We'll give it a couple of minutes and we'll come back for the black. All right, it's been a couple of minutes. We found ourselves a hammer to destroy these parts. We now have to apply some flat black paint, which we have over here. You could also use a mobile printer like this, just drop it on the parts and then print our pattern down. They're all good options. We're going to use a spray paint today. Easy way of applying bigger speckles. All right. Full pressure will give us smaller dots. Releasing pressure will give us bigger dots. And that's all we have to do here to apply our dots on our mirror. All right, and here's an example here of our pattern fully marked up.
Okay, well, as you can see here, obviously this is a recording of me, and so I'm going to introduce the next couple of videos as well. We couldn't have the cameras live here today with us, so we did do a quick recording with them a couple of weeks back with Kyle in the lab. I'm now back in our office in Seattle. But yeah, so this was us in the lab patterning the parts. And you can see it's a really quick and efficient matter here. We patterned 4 or 5 different tests in a matter of about a minute or so. And, applying this on a variety of size and scales is really just adapting the size of the spray paint. You can use different techniques as well. We've been using vinyl wrappers as well lately to do all of that. And you can see, therefore, there's different techniques to apply the pattern. All right. Let's talk about the cameras in questions that we use today. These are the brand new Phantom TMX cameras. I'm going to let Kyle tell us a little bit more about these cameras, therefore.
So today we'll be working with the TMX 7510, which is Vision Research's newest high-speed camera, and it is quite the leap forward. It's 3-fold faster than its predecessor, the V2512. And what makes this camera extra special is that it utilizes the newest CMOS sensor technology called Back-Side Illumination. So traditional CMOS sensors, what they have is a front-side illuminated sensor. So what happens is when photons impinge upon that sensor, they must go through a metal wiring architecture before hitting a photoactive substrate. So the Back-Side Illuminate technology basically flips that on its head, and those photons can immediately interact with that photoactive material, and then those electrons are collected behind the sensor. Okay, so with this type of architecture, you get better fill factor, so you can utilize that sensitivity, because when you're working at such high frame rates in such short exposure times, you need that extra sensitivity to be able to see things with such short integration times. So we're really excited today because, again, we have these unprecedented frame rates. We're able to do 76,000 frames per second at 1 megapixel. That's 1280 by 800. And the sensor can also do binning. So basically what it does is it takes neighboring 2 by 2 pixels and makes them one big pixel. And you get an immediate benefit where, for example, you can bin the sensor, for example, go down to 640 by 384, and you can be up at around 300,000 frames per second, giving you a really remarkable throughput at that resolution, okay? And this is important because these are the kind of frame rates you're going to need to characterize, for example, what we're going to look at today, brittle materials such as ceramics and glass and so on.
Well, now that we saw the benefits of these cameras and why the TMX are a leap ahead in technology, let's go ahead and set this up. So Kyle, you have the software pulled up for the PCC cameras. Let's have a look at that. Okay, so in the PCC software, we have the live view of the left and right images. I'm going to turn on some lights. We currently have a calibration object that is set up in front of our cameras. So here's our calibration object. You can see we have a live view in the software. We can turn on crosshairs to show the center of the view. All right, and I'm going to aim that calibration object at the center of both cameras. We already did a quick setup here, but essentially what we want is we want both cameras to be looking at the target aimed at the center at an angle of about 20 to 25 degrees from one another. So we separated the cameras so they would see the entire object and that it would have a 25-degree angle. So working distance from our object to the cameras times 0.4 gives us the good measuring, distance on the cameras. We already connected the cameras at the back like we saw earlier, simply connecting the F-sync and the trigger cable. So we have a pickle switch right here that will give us a hardware trigger into the cameras. We adjusted the focus and the aperture of the cameras. We can do that again here really quick. We simply open up our apertures fully. I can do it on both cameras. And now I can adjust the focus of the camera until I have the sharpest image possible. Once I hit the sharpest image, that means I have a focus right there on my calibration panel. We'll do this for both cameras to maximize or optimize our focus. And we're now going to close our apertures so that we have enough light for the test we're planning to do, but also gain depth of field. So now we have a really good location. I can get closer or further away from my object here, and I'll still be in focus and have a 3D measuring volume. Let's go ahead and build that. So we're currently set up into the center. We have a configuration from the left to right camera so that the F-sync is there. We can see at the top of the two live view, we have the left camera, master to slave from one another. Simple setup here on the right side panel of the cameras. Let's go ahead and set up maybe a session reference so that we have optimum black reference point. We optimized, therefore, the quality of our images. We're ready to take our calibration shots. We're going to put that in the center of the field of view. Again, looking at 90 degrees parallel. Let's use the synchronized image acquisition function for calibration. At the top there, you can see Sync Snapshot. Go ahead and start our Sync Snapshot mode. And we have this little window telling us or confirming that we have the master and slave cameras currently connected. we're ready to save our images into calibration folders or in our desktop Phantom folder. And we'll have a folder for our sequence of images, and then a folder for each camera for the left and right images as a series of tips. So ready to go. You can check on the Windows Explorer. And you can see here we currently have 0 images, but we're ready to start triggering. So let's go ahead and shoot the first trigger. All right, should I move this a little bit so we can see maybe the whole view? Is that a little bit better to see the calibration panel? Yep. All right. Okay, so that's shot number 1. Let's go ahead and trigger the first shot. Boom, now we have our calibration series 1. I'm gonna get a little closer to build a box in the software of where we're gonna be measuring objects. Closer, so center, closer, further away. We have 3 images taken so far. Our next image is going to be at an angle to compensate for any lens distortion that we could experience during the test. I'm going to go a little lower in this case because I changed the angle. All right. And I'm still aiming my 2 cameras at the center of my field of view. Going to be image number 4. Image number 5 is going to be with a rotation of 180 degrees. All right. We're now going to look at each camera, and we want to feed the algorithm, the calibration algorithm, but enough images to compensate for any distortion in our image. We don't want to have any artifacts at the edges of our field of view. So here's 1. I'm going to rotate 4 times, 2, 3, and 4. And you see these are dynamic images. It's a dynamic measurement, of course, with high-speed cameras, so I don't have to stay in a stable position. The image is taken very, very quickly. 1, 2, 3, and 4. All right. We have all of our images. We're ready to go into go and correlate and confirm our calibration is successful. Open up Bone Correlates. We have our calibration panel already selected here in the software. We're ready to select the left and right image. Okay, let's go ahead and click on OK to verify our calibration process. Good. About all of our images, and it's computing our results here. We have green checks indicating that we have a successful calibration all around. We can see at the bottom in the calibration result that we successfully achieved a camera angle of about 19.9 degrees. So definitely within margins between 15 and 35 degrees is what we're aiming for. And we have a measuring volume right now of 330 millimeters. So just over 12 inches box here that we can put objects in and out. And we use all of our 13 images at the bottom. You can see all image pairs were used for the calibration process. We're ready to shoot data. So let's go ahead and switch back into PCC.
So the really interesting thing about brittle materials is that you need frame rates on the order of tens of microseconds to be able to capture such an event, because crack propagation is really quick. So we have right now the camera set up at basically a full resolution at, I think it's 76,000 frames per second. So we're kind of curious to see how this will do. And if it isn't fast enough to capture this glass crack propagation event, then we can always window down the sensor and go up in our frame rate. So what I'm going to do is I'm going to strike this piece of glass from the back, and we're going to study that crack propagation in the material. Okay. So how is our trigger position right now? So that means once we get a trigger signal, everything before the trigger will be saved to the buffer. So once I hit the material, you can wait a second and then send a trigger.
Okay.
All right. All right. So now I'm going to strike it. 3, 2, 1. A little bit more aggressive than I thought it was going to be, but you know.
Okay. Let's see what we get here. We're going to go in playback mode. And looks like we have, let's lock up our replay so we can look at both cameras. All right, looks like we definitely are pre-impact here and impact. So we need a couple seconds before that and a couple seconds after it too. Great, let's pause there. That's probably going to be enough for analysis. Let's go backward. Let's go ahead and mark the beginning of our project. Let's save our data. All right, this is going to be test number 1.
Can we save it as a city first? So
Yep.
we have all the raw data.
Absolutely, that sounds like a good plan. Here we are. You can see the progress down at the bottom here for both cameras. It's going to be maybe a minute. I'll prepare here a new project in our Golden Correlate environment, and we're going to get ready to import the images, calibration result file. See where we're at. All right, the syn is done here. Let's now save TIFF stack. We're saving TIFF in 8 bits to import in the Aramis software. Again. All right, let's save left and right images and indentation numbers of 6 total padded numbers. Save. Same for the right cameras. And our TIFF images are coming up. It's going to be another little minute here.
Let me just check that the tips are actually in there.
Sure. Phantom tests 1. Left.
That CHD file that you have in there, if you go to the top, what that is actually a metadata file. So when you save as a TIFF, the images actually shed all their metadata with respect to the exposure time, the frame rate, but that CHD file, let's say if you wanted to recreate a cine file, you would have to import all those TIFF images and that CHD file, and then you can restore the original cine file format.
Yeah, it's actually possible. We've worked with a couple of our customers to import the CHD files and import the metadata in your Aramis project so you can get a little bit more information about the exposure or the frame rate at which you are running in an automated kind of fashion. So these are all things that are in there. At least you're saving the data. And ready to import. Okay, and let's go back into BCC and let's do another shot while this is importing. Capture mode, CSR done.
We are now at 115,000 frames per second at a resolution of 768 by 512. And now I'm going to give it a firmer whack here. And I'm going to ask for you to trigger that.
Yep.
And okay. So I'm going to hit. You're going to wait just a second and then press record. All right. So 3, 2, 1.
All right, that was a good whack. All right, let's go and take a look here at our replay. All right, we're going to see the reconstruction of the pieces. Look at that. We're going backwards, but this is a really good shot.
See how many frames we get in this propagation. It's a nice center hit.
That looks good, I think.
Yeah, can we walk it back just before it breaks?
Yeah, I'm just going to set that as our end trigger. And let's go back to before break. Let's save our SYN. That's good.
You're on tip 8 right now?
Yep. We'll do this and then we'll go back to SYN.
Perfect.
We'll have both. All right, halfway through.
Good.
All right, so we're done with saving the TIFF, so we can import them into Home Correlate. In the meantime, let's go ahead and save our Cine files. Okay. All right. Save. Okay, so we have our previous shot in here and our latest shot down there in the second folder. Let's go ahead and, this is computing here from our first shot. We had 7,000 stages. Let's do a new project and start importing that data. And we're going to go ahead and import from our glass impact test, the second series, left and then right. Test 1 and second full. All we have to do is select the first image of this series and the software automatically detects the rest of the images and will import all of our data into a nice replayable time. So it's doing a pretty good job at computing and saving data all at the same time here. We have a little bit of everything going on. All right, so here's our complete destruction of the mirror piece. And let's go and have a look. Maybe
you can see the bulge.
Yeah. All right. Let's go ahead and create a surface component here and inspect this entire area. Probably don't need the whole glass piece, but let's do it anyways. And let's compute that on our 1,000 stages. Computing this full failure. And probably another 5 or 10 seconds here. Oh, slowing down because of the impact.
Oh, really fast. Yeah.
All right, let's see. We have our glass panel here. And yeah, it looks like we're going to get the little panels coming out pretty well. Let's have a look first at strains. Ooh, look at that.
Love it.
All right, let's calculate the strains on all of our stages really quick.
What's our facets?
We're at 19. And let's take a look at this as a replay. So it's going to go up to about, looks like we could probably switch to percentages here. There it is, preferences. And let's switch to percentages. Okay, so I think we probably have, all the way up to 5 or 6 or 8% strain maybe. Let's go from 0 to 8%. Look at that beautiful data set.
That made my day.
All right, let's drop a couple of labels here because that looks like it's a pretty nice little peak right there. And let's take a look at that diagram over the impact. And you can see that we have a couple of really nice points just before the impact here. So this right there sounds like a pretty nice area to go and zoom into. So let's create a stage range for pre-impact. And let's go and have a look at what's going on right there in that pre-impact zone. Okay. It looks like we're at much lower strain, but that makes sense because we're probably just, in kind of plastic or elastic, deformation. It's a little bit noisy, but you can see it coming up. Yeah, there you go. So you can see the pre-impact zone really well in this area. Okay. Well, there's a couple more things that seem to be of interest here. You said, Kyle, it looks like there was bulging. Let's have a look at displacement in the Z direction. And you were definitely right. Look at that bulge.
It's pretty impressive.
All right, let's take a look again at a scaling that's a little bit more
You just
global.
don't ever think about glass bulging before it cracks. You always think about, it's so fast and it's just think it cracks.
And I mean, there's a couple of millimeters here of displacement out of plane before it breaks. And it's still zero all around here. So, there is not a lot of rigid body from the outside. This is definitely local bulging. Let's make that a little nicer even for visualization purpose. And let's extrapolate the Z displacement here and project that in the Z plane. Maybe let's project it times 50. Really see, what's the shape of the glass here. All right, look at that. We really can see, here the bulge is pretty uniform, very symmetrical all around your impact. Remind yourself, that this is an exaggerated representation times 50, but you can see perfect center of impact right there. Let's take a couple of shots from this. Let's save this view. So pre-impact displacement out of plane displacements times 50. Keep that shot in our report. I think it's worth going back to the strain here that we were looking at initially. So let's go and have a look at these strains again. All right, and we had a label at the center location. Let's go back to the global view, 0 to 8%. And let's make sure that we also save this as an overlay on top of our high-speed images and save this as a video. So major strain as a video. And this is going to be now let's make this a 10-second replay of our event. Perfect. All right, we now have different reports here. Let's export, our two videos of major strains and displacement as MP4s. There they are, major strain and displacement Z with image mapping. Our second application.
All right. I'm just going to take a quick break here to acknowledge the fact that we just ran out of time technically. If you guys want to stay, we are now going to move into the second application, was the ballistic test, where we binned the sensor into an even faster frame rate. And this one's still a little shorter. It's about 7 minutes. But if you want to stick around with us, or if you have questions, you can start asking them in the Q&A section or in the chat. We're going to start answering them right now in the chat if you want, or at the end of the second portion of this video. All right. Thanks.
Here, going from the standard resolution on the glass crack propagation, and we're now going to do an experiment when we shoot through a bulb that we patterned earlier. We're going to switch to binning so we can go really fast here and also track our projectile as we do this. So here we are, binning mode.
What a really nice field of view already we have there. So right now we are binned and we have 640 by 348, and I can go 300,000 frames a second, which is a really nice rate. So I'm going to keep it nice and bright so we can see our field of view. And we are going to basically call this our third calibration, correct?
Yeah.
So now we are in bin mode.
Perfect.
And we are ready to go.
Image number 1. Further away. Back from center, but at an angle. Back to looking at each camera. So we're going to look at the left camera. One, 2, 3, 4. We have all of our calibration images. Okay, so we have the pair camera here, which we just calibrated right there to the right on our tripod. And all we have to do is rotate the camera back to our field of view and back on our line, on our light here, the light bulb. And gotta make sure that everything's locked down.
Charles would be kind enough to turn that light back on, the frontmost light. All right. So it looks like we have plenty of light here. So what I'm going to do is actually lower the exposure time down to, with this camera, you have the opportunity to go sub 100 nanoseconds. So what I'm going to do here is actually go down to, let's see what 1 microsecond looks like. That's pretty good. I'm going to do a CSR. And I'm going to move the trigger position to the very center so that when we hear the bang, we can press the go switch. And I'm going to make sure my slave camera has the right trigger position. And we are ready to do our shot. I'm going to run the fire into our light bulb here and do our image correlation. Charles, are you ready?
I am ready.
3, 2, 1. All right, that was satisfying. Looks like we just have just the filament left over and actually pristine condition, surprisingly. Charles can come out from behind the plant. That was great. That popped.
Let's go and have a look. Let's go straight to our trigger here. And let's go backward a few seconds. Actually, we might need to go a little faster because this is at, 500,000 pictures per second. Look at that. Look at that. Boom. It looks absolutely fantastic. Look at that. Let's go ahead and save. Save sin. And let's go ahead and save our TIFF stack as well. All right. And let's go ahead and start importing our data here. And we're going to use our calibration number 2, bend mode. Okay, let's have a look here. So let's manage our stage right in and make sure that we have the right timestamps. So we're going to import our right frequency. We're currently at how much, Kyle? 300,000. We are at 3 microsecond. Frame rate is now imported. We could look at our timeline in time. And we can now create our surface component. Look at that. We're going to go down in size here to 1610 and select all of our light bulb. All right, let's compute that on all of our stages. And even though we actually did not have any markings on the marble, we can see that what we shot here actually has some contrast. So let's see if we can pick up some of it and maybe measure the speed of the projectile before it hits the light bulb. You'll notice here that there's it looks like there's a lot of noise in the back. We're currently in lighten image mapping mode, which just helps us improve the contrast, kind of see what's in the background there. It's not affecting the processing. Doesn't matter. It's just there to help us see a little bit better. Let's go and scale our project for all of our stages. So we're really going to have a nice little replay here. Let's see what we get below 4%, maybe 0 to 4%.
There you go.
Let's turn back down the light and image mapping also, which is kind of tricking our eyes. Let's see what we're seeing here on the left edge is probably just due to the selection. It's in the darkness a little bit. You can see the tip right there of the crack, as well as in here. I think if we inspect these two locations, we're definitely going to see a nice little rise here before it actually broke. We actually need a little bit more. There it is. 0 to 2%. There it is. But the XY is really going to show us where the crack is about to appear. If you look here, you can see this showing up.
Oh, wow. Yeah.
Before we get the crack.
really visually.
Right. So there's a lot of strain there at first. That strain leads to
Yep.
eventual crack formation.
Correct. Look at that here as the crack is starting to appear
Really
in the
nice.
pixels.
All right, this is it for the two applications that we want to show you live. So you saw here in full resolution and in binning mode a complete workflow of setup, calibration, acquisition. And we passed the 30-minute mark, unfortunately, but we still did, all of that during just half a day, and then some more. So this was the result that we saw from the first application with the crack, the strain propagation on the glass here. You can see the hammer impact from the back, and every crack really showing up. Then, we just saw the live demo. I wanted to just tell you that we did some other shots. If you have interest in those, we can talk about some of those other applications afterwards.
All right,
But we also did another shot here. Just going to cut the sound. We did another shot with an impact from the side here. So you can see the data will play, and we can look at the data together if anybody's interested in that. And then we also did an impact on a phone, and this one looked really good. Took a couple of shots for Kyle to aim at the right spot, but when we got it, we got it. And so we can see here the bulge of the phone. So we're looking at displacements and strains during the impact. And again, we can see the glass really start to shatter thanks to the speeds at which we're recording here. And we're also getting strain responses here along that notch. And again, we can see really the growth of the strains before failure. So these were really interesting shots. I think we have here a camera that's very interesting as it opens up a brand new different areas of research at really high speeds with still enough sensitivity to shoot at these speeds. And compared to existing cameras that do millions of frames per second, because there's a couple of cameras that do that, this camera has a lot of RAM on board, and you can record for a long period of time. Right now, you kind of have to make a decision before the TMX. Either you want to have a lower resolution for a long period of time, or you want to have a higher resolution with just 180 frames. This opens up a whole area where there's an in-between here where you can go into the hundreds of thousands of frames per second into almost 1 million frames per second with still some decent resolution. So it's a really, really good mix. And I think it's a camera that is perfect for digital image correlation. We had a lot of requests to prove that this would work out. And so, we're glad that it did, and we're glad that we were able to do all of this in just a couple of hours. And hopefully you guys enjoyed this 40-minute presentation with some live examples. We're going to go ahead into Q&A right now. Kyle's going to join me back, and if you have questions, don't hesitate to ask them over there. We're going to stay around here probably until the next 15 minutes, so it's going to turn up into an hour. But go ahead and ask questions at will.
All right, thank you, Charles. I'll go ahead and read the first couple questions to you guys. This first one, either one of you could really answer it. Christoph is asking if it would be possible to borrow this system for research measurements at the university for a day or two.
That's a good question. So we are totally able to rent these equipment. So if you don't want to purchase the whole thing, yes, of course, that can be very expensive. But you can rent the systems. We don't loan them for free. We can do demonstrations if you need to prove out the technology on a test. But we can certainly loan them for a couple of days or a couple of weeks, depending on the durations of your test campaign. And we can help you out, obviously, with figuring out exactly what you need for that testing, so that you don't have to waste a lot of time in figuring out your methodology. We're here to help you develop the whole process together.
Great. This one is for Charles again. Stephen is asking, so no GOM camera unit used, just the process of calibration, tracking, and Trilion software to crunch the data.
Yep, that's correct. So we are using the cameras here from the manufacturer, from Phantom, and we are processing everything in the GOM environment, so in Trilion software as a whole. So it's hardware and software, I guess, separated. Now, we do have a little bit of of hardware that comes from the 3D calibration. So you still need a panel, you still need some calibration, some synchronization between cameras and things like that. But globally, the cameras are not GOM cameras. The goal of using these cameras, though, is that we vet them. So we do test them out to make sure that we can do a certification with them and that they pass the test. So sensor is good enough.
All right. Travis is asking, what are some difficulties or challenge areas you've noticed in using the system? Charles or Kyle, could you guys elaborate on that?
I can add some comments on that. I would say that some of the difficulties, especially in the in the scope of what we tested, was basically, since these are brittle materials, it's difficult to exactly know what your camera parameters should be before you test it. So we had to do a little bit of trial and error to actually see what are the idealized camera parameters in terms of, again, frame rate, exposure time, and resolution, and all that mix. So that's one of the difficulties that you would run into. So hopefully the test you're doing is something that could be done over a series of times. And the other thing too is, you're going really quickly, right? So you're imaging up at 300,000 frames per second, or maybe upwards of 500,000, right? So you want to make sure you have the proper settings for the camera and also your lights. So, high-speed imaging is always a balance between a lot of different things: aperture, exposure time, the number and angle of your lights, and all that stuff. So you really got to pay close attention to kind of the whole system together to get the best results.
Yeah, I'll add two more things in terms of handling the cameras as a camera pair for DIC. There's certainly the fact that these cameras are not light. They're quite heavy. That was somewhat of a challenge to mount them properly and make sure that they would stay in calibrated well, because otherwise, as soon as you move the cameras, even just from one side to the other, then they would move or decalibrate. So that's not something that we want, obviously, to maintain 3D calibration. So that was certainly a challenge, was the weight and mounting them properly. We do have, a couple of mounts, and we've got experience with cameras that are heavy, but these were definitely the heaviest cameras I've ever used. And so that was part of it. So, handling them with the tripods and everything was a little bit of a challenge. The other thing I would mention is actually resolution. We talked a little bit about the binning, but also about the full resolution. And when we talk about the gigapixels per second throughput, so saying that it goes up to 75,000 gigapixels per second, that's true at those max numbers, but we kind of found out also that especially for DIC, cropping does not necessarily mean that you're gaining speed for a smaller resolution. There's kind of steps, and especially in the height. So if you crop in the height, afterwards if you crop the width, it won't really give you more or less speed. So there's really kind of steps where, you're going to maintain the maximum throughput if you're at the maximum resolution width and height for that block. And then if you start cropping in one direction or the other, you're not going to gain any faster speed until you go to the next crop session. So there's a little bit of notch, and that's, that was a little bit of one of the challenges that we experienced. So for the AC, we found a couple of sweet spots where resolution was optimal for the speed. There was actually also a question from Stephen Reynolds about the lights that we use for the ballistic shots. And I answered there, but just so we have the answer live too. So we use the 1 kilowatt lights with the big projector that you saw in the videos, and 2 smaller GS-VITEC lights. We use just the GS-VITEC lights for the glass, so that was sufficient. And these each are 12,000 lumens, if I'm not wrong. And the 1 kilowatt light, I actually don't know how much lumen it projects, but it's definitely very bright. It's probably, I'd say, about 5 times brighter than one of those little GS-VITEC lights, maybe even more, Kyle.
Yeah, they're definitely brighter, and they cover a larger field of view. So the lights, yeah, we used, I think it was the 4438 IES lights, and they're kind of ideal for if you're doing some high-speed imaging with, let's say, 0.5 meter to 1 meter fields of view, whereas the GS-VITECs are kind of for like 0.5 meter and down. So definitely enough light to do, sub 1 microsecond imaging for sure. And if you have a pair of them, then it's, there's really no issue across the whole exposure range.
Okay. Ryan is asking what the price of the GOM software is.
Yeah, that's a good question. So Ryan, I'd start by saying, we'll always look at what exactly you're trying to do to figure out what's the right software module that you need. But globally, the software is going to come in around 20 to 30,000, depending on what kind of other accessories you need. So you're going to need some calibration. You're going to need some mounting. You're going to need, the kit as a whole. So we rarely just, sell the software. If that's what you want, we can make that happen. But we'll usually have the accessories that you need to turn the camera or the cameras into a DIC system, a turnkey solution, so that you can actually do measurements with it. That being said, because we have a lot of questions, especially in the academic markets, I'm not sure where you're from, Ryan, but if you want to do digital image correlation, there's always a doorway to enter this world, and that's GOM Correlate. This software is completely free. We give our software for 2D analysis, so if you only have one camera, be it high speed or lower speed, you can do the processing that you saw today here with just a single camera. You don't have any out-of-plane displacement, of course, but if the motion is just in plane, or most of your displacements is in plane, then you could use that. We have a lot of people that are trying to, go and do it in MATLAB or use NCore and other kinds of Python libraries. I don't want to say it's a terrible idea, but I do think that it's not really relevant. You're going to spend a lot of time trying to develop your own codes to use these libraries when you have a GUI interface that is free to use. We have more and more universities that are also teaching their students how to use GOM Correlate in their strain gauge lab. And so every year we have a couple of hundreds of students in different universities across the state that have learned at least an industrial platform to do the analysis. And again, that software is completely free. If you go on our website, you can download GOM Correlate and process any 2D sets of images or videos. And that's a really good start. Before you talk about 3D and calibrations and all of that, GOM Correlate is a good option.
Thank you, Charles. Chris Worrell is asking, are there any limitations using this underwater for looking at underwater explosion effect on ship hulls?
That's a good question. So yes and no. I mean, obviously the limitations are the cameras are not waterproof. If you manage to make an enclosure for the cameras to go underwater, or if you're filming like for an aquarium or something, I'm guessing, it would be in a lab. But if you do something like that, then yeah, there's no limitations of measuring something that's in water. If there's issues in the images, if there's shockwaves and things, you might have problems. But if we have teams that did this in situ, in vivo testing of like art valves, and the kind of pig valves were in an aquarium, and they were filming through the glass panel on the edge, looking through the water at the valve. So that's something that would be possible and scalable. I mean, it would have to be defined as a methodology. I don't know that we've done a large field of view with high-speed cameras on the water, but I don't see technical issues. There might be problems along the way, but I don't see why it wouldn't be possible.
Yeah, and we also do a lot of underwater work, for a variety of different applications, and we do have some partners that are really good at wrapping up the cameras into some, water-resistant enclosures. So, don't hesitate to reach out, and we can kind of direct you to the people to talk to.
Michelle Fan is asking, what is the starting price for a TMX 7510 camera?
It depends on the model you pick and all of that, but I think the ballpark is around 220, 225,000, something like that.
All right, thank you, Charles. Legna has left a question here as well. It would be interesting to see strain mapping during glass breakage when the glass has surface flaws, specifically if you don't have a quick event like a bullet passing through glass, but an overall applied force. The breakage on a flawed surface would still be a fast event, and it would be interesting to see the live breakage. Charles or Kyle, do you have any input on this?
I think Ligna is trying to encourage Charles and I to do some more testing, which I think we happily will accept. But yeah, I would say that from my perspective, this whole area of looking at glass break is kind of new to us because we can do it kind of properly now with the right equipment. So we already have had some really nice inquiries into these kinds of questions. So yeah, I also have the same interest in these kind of questions. So that's a good question.
Yeah. I would also add on that point, actually, just like Kyle was saying, now that we have the right tool, but just like we were saying earlier, the current cameras to do kind of glass measurements are really fast, but really and high resolution, but not a long duration. You can do about 180 frames at a couple of million pictures per second, but that's it. You only have 180 frames, whereas this camera here can record for a couple of seconds. And that really kind of ties into what you said, where, it might be a low load, but you can still catch the dynamic event when it happens because you have a long recording duration. So really, these cameras would work very well for the kind of application you're describing, I believe.
Thanks. Travis is asking, have you cross-referenced the data you get from this system and data you get from analog-based data collection systems, and notice any discrepancies between what data the cameras collect versus what sensors collect?
We have not. I don't know about you, Kyle, but we did not compare the 3D-DIC system with this. We don't have the equipment that goes that fast to go at 300,000 frames per second. So.
I can speak a little bit to that because we've had some questions about that in the past, and for the most part, like what we see is, people going from, traditional ways of measuring strain and vibration to the more modern non-contact way of using imaging, right? And I have done experiments where, we looked at a tuning fork, right? And we had a accelerometer on the tip of the tuning fork, and you can basically correlate and compare the data measured from, an accelerometer with the data extrapolated from digital images. So I do have data on that. But did I dig very deep into any deltas in the data? No, I haven't done that. But it's certainly possible. The shortcomings of putting a strain gauge or an accelerometer on a tuning fork is you intrinsically perturb the system, right? You change the resonance frequency, the spring constants, and all that stuff. So we definitely see a lot more people going the digital image correlation route rather than coupling their systems with accelerometers. Because, from our perspective, we're the camera manufacturer, we also support people who like to synchronize their data, for example, accelerometers and strain gauges with their digital images. And we kind of see a transition away from that, right? Less and less people ask me to help them synchronize their analog DAC data with the images, and more people are interested in doing the image correlation work. I don't know if that exactly answered your question, but yeah, there's definitely some interest in that to ask that question.
All right, thanks. Okay, well, it looks like that's all the questions for now. I can turn it over to Charles for any closing statements.
Well, thank you very much for sticking with us for after all. Hopefully the amount of content that we have to show you was enticing enough. Otherwise, we would have lost you. So thank you for staying around, and sorry for just booking 30 minutes in your day. But yeah, I think these cameras are really opening a different segment in the high-speed market. And if what you're trying to do requires this, then we're here to help you out. We're happy to continue doing demonstrations. We're here to come and bring the cameras on site if you need to. We can bring a whole system, test the methodology out together before you just make a commitment to a system like that, be it for a rental or for a purchase of a system. We integrate and bring a turnkey solution, so that's what we're here for. If you have technical questions for both me or Kyle, feel free to write to us. We're going to reach out to pretty much everybody. We're going to share the recording anyway of today's videos with you guys. Thanks again for tuning with us, and we'll see you in the next webinar.